Okay, so let's just start. If you remember last class, we have discussed about spray characterization, spray parameter, in which we have discussed that there are say, 4 or 5 spray parameters that is really very important, and we need to characterize it um, before it can integrate with the engine. Okay, because spray characterizations, in fact, it is a affects the engine performance and combustion. So in which we discussed about what is the spray angle, breakup length, droplet size distribution, and the spray tip penetration. We also discussed that how experimentally we can measure all these parameters. Then we started about common air direct injection system. That is what we have right now in the advanced injection system, in which we have a lot of flexibility. Okay, um, we have a flexibility to vary the injection timing. Okay, injection pressure, injection quantity, a fuel quantity, and the multiple fuel injection in one side. So all there are this flexibility we have that was not available in our previous older injection system, that is the mechanical fuel injection system. Here we have a flexibility to, and then we also discussed about schematic of the CRDI system. Here we have one is the high pressure fuel pump, second is the fuel filter, third one is the fuel tank, fourth is the low pressure fuel pump, then fifth rail, sixth is the fuel pressure sensor, eighth is the fuel pressure control valve, seven is the injector. So, and then we discussed that how the fuel uh, flow through the pipelines before it reach to the injector. So that's what we have discussed in our last class. Then we stopped at a point to discuss that how we can vary the fuel injection pressure. Okay, from the 200 bar to maximum pressure, that depends upon the hardware and the software capability of the fuel injection system. That normally it is more than 1500 bar or up to 2000 bar, we can say. So now there are different kind. There are two ways, or probably we can say there are two models of the CRDI system. One is called first generation, that was initially when it was invented or when it was integrated with the engine. Now we have a more advanced CRDI system that is called second generation CRDI system. So let us discuss with the first of all the first generation CRDI system. Okay, it all depends in between these two generations. It depends upon the how the fuel pump is the difference in the fuel pump and the algorithm or the control system, how if we are controlling the things. Otherwise the rest of the things is going to be the same. So in the first generation, what happens, the fuel pump always works at the higher pressure or the maximum pressure. Let us suppose this fuel pump has a capability to pressurize the fuel at 1500 bar. So this fuel pump will always pressurize the fuel at the maximum value, that is 1500 bar, and it will send it to the fuel rail, irrespective of the demand of the fuel injection pressure. Okay, so now let us suppose if there is a no fuel is returning back from the rail. Okay, then what will happen, that in the fuel rail, the this, or we can say in that way, this sensor number 6, that is sensing the pressure, fuel pressure in the rail. This sensor will sense the pressure of the fuel in this rail. That is what the maximum pressure of the fuel pump, that is 1500 bar. But now let us suppose we want to uh, have a fuel injection pressure, let's suppose 500 bar. Then how we are going to get the 500 bar? So what will happen? Then user will define that the fuel injection pressure needs to be 500 bar. User, why I am using the term user? Because I am supposing that we are doing the experiments in the laboratory in the open control mode, not in the closed mode control system. Closed mode control systems, or we can say in the vehicle conditions, engine will, ECU will sense from the different input parameters that what should be the fuel injection pressure. But here, let us suppose we are doing the experiments and then everything in the open condition, open loop condition. So user is defining the fuel injection pressure here at 500 bar. Okay, how we are going to get the 500 bar? So what will happen once user will define that 500 fuel injection pressure I need, then that information will go to the ECU that we need to inject the fuel injection pressure, and that it means at here the fuel injection pressure has to be 500 bar. Then what ECU will do, it will control the this sensor. This sensor is nothing but it is a kind of the solenoid based sensor. Okay, and it this opening is the opening area is going to depend upon the actuation signals. Okay, so ECU it will send the signals to the sensor 8 that open this area. Partially it opens this area. Then what will happen? The fuel in the rail, whatever the fuel in the rail will flow from the bypass line, and it will go to the your fuel tank. So in that way, what will happen and how much it has to be open? Okay, because here in the rail we need to maintain the pressure at 500 bar. So dependingly, accordingly, this opening area is going to be open, and simultaneously it will sense the value of sensor 6, that is the pressure signal. So ECU will direct to the sensor 8 to open the this area, and simultaneously it will sense the value from sensor 6, that is the pressure sensor. By these two combination of the sensor, the partially opening area is going to be fixed until the pressure drop in the rail at the 500 bar. So in that way, we can get the 500 bar pressure, even though here the pressure is coming higher, but most of the fuel, or depending upon the opening area, is returning back to your rail. Similarly, we want to have 800 bar fuel injection pressure. So then ECU will close that areas, and in that way the fuel injection pressure in this rail is going to be increased, and then we are going to get the maintain at 800 bar. So with the help of sensor 6, that will give you the instantaneous pressure in the fuel rail, and the sensor 8, that is pressure control valve, that is responsible to open this return line. This combination of, by using this combination of sensor 6 and sensor 8, we are going to control the fuel injection pressure that can vary from the minimum value to the maximum values. That is what around or approximately 200 bar to 1500 or 1800 bar. Now that's the way we can control the fuel injection pressure. Now when we have to inject, that is the SOI, start of injection. Start of the injection, it is ECU, obviously ECU is going to be controlled. That let us suppose we want to inject the SOI, or we want to have fuel injection takes place at around 10 degree before top dead center, then this information has to be fixed, or this information has to be supplied to the ECU, and accordingly ECU will get the input signals from the engine crankshaft and camshaft, and it will find it out when the piston is reaching at the 10 degree before top dead center in the compression stroke. At that time, the ECU will send the signals to the injector. Injector is a solenoid based injector. So as soon as injector is going to receive the signals here, the plunger will move up and the fuel injection is going to be takes place. So in that way, it can control the start of the injection. Since we have a control over when we want to open the injector, so that's why we can send the signals 2-3 times in one cycle to the injector to open it. And in that way, we can control the multiple fuel injection system also. But it's not like that we can open and close several times because there is a time limitations. This is the hardware. Hardware has its own delay time also, and then the duration is also limited under which in which we have to inject the fuel. So therefore, depending upon the response time of the hardware and the control system, it is going to be dependent that how many fuel injections or we can have in one cycle. Okay, and therefore I told that sometimes in any engine you may find it out there are three times fuel injection is taking place, or in sometimes there are 5 fuel injection times is taking place in one cycle. It all depends upon the optimization and the capability of the hardware and the response time. In that way, your common in the very basic way I just try to explain that we can control the all the flexibility or all the parameters in common air direct injection system. This injector is completely different, okay, from what we have um, discussed in the port fuel injection system. Because here the injector has to be operate under high pressure, and also it is going to inject the fuel under the different conditions. So this kind of the injector is called peak and hold injector. Peak and hold injector. It means during the opening it requires a high current. So initially your hardware has to be capable to provide such a high peak initially, so that injector can opens, because initially the inertia is very high. So to open the injector you need to apply more power, so the current will be very high, and then once it is opens, then the maximum current is going to fall down and it is going to be then lower than the max is going to be constant. That is called peak. That is what we need, very high power current, and then hold. Hold it means it is going to come back and then going to be remains constant as long as it is the fuel injection has to be take place. So this kind of the injector, it requires a different kind of the driver which can which is capable to provide such a high current also. Whereas in the port fuel injection system, it is a very simple kind of the things. Even a square pulse of having 5 volt and around maximum 1 or 1.2 ampere current will be sufficient to actuate the injector. But in the CRDI systems or even in the GDI systems, it requires a different driver to operate this injector. So by controlling the sensor 8 and getting the feedback from sensor 6, it is possible to vary the fuel injection pressure as per the optimization. Then controlling the injector, okay, it is possible to vary the fuel injection timing or multiple injection. So that's the why it can be done. But in the first generations, what we have observed that the fuel has to be a pump has to be operated always at the higher conditions, that it is pressurizing the fuel always at the maximum value, even though we require the lower fuel injection pressure. So it means we are wasting the energy here. So in the second generation, CRDA systems, this has been changed, and then the control system has been developed in such a way that whatever the fuel injection pressure is required here, that is what it going to be pressurized also from the fuel pump. That is based on the how in the fuel pump system itself, because and that is possible if because this kind of the pump is the this pump is the piston assembly kind of the pump. So if you require a lower pressure, then we are not going to compress the fuel up to the maximum stroke length, and this opening of the fuel is going to be open even much earlier before the piston in the pump reach at the top dead center. So the fuel is not going to be pressurized as it is at to the max, and then in that way, so we can control the fuel injection pressure in the pump itself, and then the pump is not required to run always at the maximum value, but uh, it is only going to compress the fuel as it is required. So because the rail is going to be act as an accumulator, okay, and then we control the fuel injection pressure with the help of the 6 and 8. The fuel injection pressure, in fact, it is going to be the independent of the engine speed. Whatever the engine speed, it does not matter. It is always because here the fuel pressure is already accumulated here, so we can vary the fuel injection pressure as it is um, required. So that's the way the a simple control systems. That's the way in the very simple way I can explain to you that how the driver works and controls the whole common and direct injection system to get the variable fuel injection system, a variable fuel injection pressure, variable injection timing, or multiple injection system. Okay. So that's all about the CRDI system. If you have any questions, please ask from here. Any question here? How the CRDI system works, okay, or how the we are controlling the fuel injection parameters of the fuel injection pressure or timing. Do you have any question? No, that's right. That's really very good. As I told you, this all these things I have taken. I'm explaining you from the digital engine management book. That's really very good. I have 2 3 times I have told. I would request all of you to read that book at least whenever you find time. That's really going to give you the very insight view about how the control system works. Okay, before moving to the next part, I would like to make an announcement that tomorrow, that is 10 to 12, you have a class of ATF 10 to 12. So tomorrow, instead of Professor Saurabh Mitra, I will take the class from 10 to 12. It is because that I will be not available in the next week. So therefore, tomorrow I will take the class, and then the Professor Saurabh will be available on the Thursday and Monday and even Tuesday also. And the next week onwards, Thursday, I will start the class. So tomorrow I will take the class from 10 to 12. Okay, let's move ahead. Okay, so this part I think we have already discussed also, that how the system is here, and all these things we have already discussed. So till now, if you can summarize that what are the things we have discussed. We have discussed after the mid-semester exam or the first test. Probably we have discussed in details about the port fuel injection system and very details. Then we have discussed about gasoline direct injection system, and these two technology we used to um, inject the fuel in the spark ignition engine. We also have discussed that how to control the air fuel ratio in the SI engine. Then after that, we started discussing about common and direct injection system that is used to inject the fuel in CI engine, how it works, what are these hardwares, what is the flexibility, and what are the benefits of the CRDS system. Okay, so that's fine. So it means with all these discussions, at least now you have knowledge from this class to how to prepare the air fuel mixture inside the combustion chamber. Okay. Now, what we are going to do now, we are going to discuss at this point about the combustion. That once the air fuel forms inside the combustion chamber, so how the combustion and then after that when it combustion starts either with the help of the spark plug in case of the SI engine or with the help of the compression in the case of CI engine. Once the combustion starts, then what happens? And what are the abnormal combustion? Okay, these two things we are going to discuss now. Obviously, we are not going to discuss in two details, okay, but I will try to give the overview information because it's not possible to cover all the combustions part in a half of the class. So, but however, I will try to give you the overview of the combustion from SI and CI engine and some important parts, something important that is really very important at your level. Okay. So what we are going to discuss? Half of you, no, not half of you, almost two-thirds students, yes. Now they have done the experiments in which they have experience to do or to measure the in cylinder pressure, okay, and they analyze the P theta curve. So let me discuss the combustion in SI engine, okay. And here, what I'm assuming that all of you is very well familiar with the how the air fuel mixing or how the air fuel mix with each other and form a combustible mixture into the combustion chamber. And then second thing is that towards the end, once the fuel and air comes into the combustion chamber during the intake stroke, okay, and then the compression stroke starts. So towards the end of compression stroke, a spark is going to be takes place, okay, or external energy is going to be supplied with the help of the spark that will initiate the combustion. Okay, once the spark is created towards the end of the compression stroke, okay, then what will happen? The flip will be developed and it will progress across across the combustion chamber and it will consume all the combustible mixture. I'm assuming that the thermodynamic conditions and the mixtures is well within the combustible limit. So once the combustion starts and then the pressure inside the combustion chamber is going to be increased, it will reach at the max and then again it will fall down. Now, if we look this curve very carefully, then what we are going to get it. In our theory class, I have already discussed that how to measure the fuel, how to measure the P theta diagram, pressure or variation of pressure variation inside the combustion chamber with respect to the crank angle. That we have already discussed in our previous I think when in the before the first test, I think so, or in the just after the first test, we have already discussed about how to measure the P theta or in cylinder pressure variations. Okay, what are the hardware do we need? How the hardware works? What are the sensors we require? How the sensor works, talk with each other, and it display the P theta. That is what one of the curve I have plotted here. And then I am going to discuss about some of the interesting facts in the SI engine combustion. So now we see the x-axis and the y-axis. On the y-axis, we have a pressure, that is in cylinder pressure. On the x-axis, we have a crank angle. 0, it is what representing, it is a combustion TDC. Combustion TDC, before that, it is, now if you see the 8, 20, 40, it is a before top dead center. So now it's very common, if you see the pitch heater diagram in any book or any research paper, you will not find that this x-axis has been represented from 0 to 720 degree crank angle or minus 360 to 360, because we are not going to get anything new information. So therefore, it is always customary or it is beneficial to plot the curve within a short range of crank angle over the 720 degree, so that we can extract the useful information clearly. Therefore, on the y-x-axis, the crank angle has been varied from minus 100 degree crank angle to 80 degree crank angle. Or in other words, 100 degree before top dead center to 80 degree after top dead center. 0 is representing the top dead center. So minus 100, minus 100 to 0. It is what? The piston is moving up during the compression stroke. Then what you are seeing here, that after piston reaches at about 18 degree before top dead center, a spark is created. Okay, and then up to the point B, that is 8 degree before top dead center, there is no difference between this thick line and the dash line. What is this dash line? We haven't covered. This dash line, it is representing or it is written there motoring. The dash line is representing the motoring pressure. I hope you remember that what is the motoring pressure. Those who have already done the experiments, they know very well about what is the motoring pressure. Motoring pressure, it means the engine is rotating without the firing inside the combustion chamber, or engine is rotating with the external power, and therefore it is called motoring pressure. You have already seen in the experiments that motoring pressure more or less is symmetric across the top dead center. Yeah, so now let's come on. When fuel and air mixed with each other and compressed inside the combustion chamber, when piston is at about A, that is 18 degree before top dead center, a spark is created. But if you see that there is no difference between the firing pressure curve, that is thick line, and the motoring pressure curve. But after the point B, these two curves are going to deviate with each other, and the thick line, that is the firing pressure, is reaching at the max, that is at point C, that is about 15 degree after top dead center, and then after that pressure inside the combustion chamber falls down. Okay, that is what we can see from here. Now, question 8. Why, if a spark is created at point A, why not the pressure between the firing pressure and motoring pressure are deviating with each other? Why there is an overlap between A and B? It is because that as soon as when you create the spark, the combustion is not going to be initiated at this point itself. Okay, there is a time lag between the spark timing and the start of the combustion. A is representing the spark timing and B is representing the start of the combustion. So there is a time lag. This time lag depends upon the several factors that we are not going to discuss. So it means the combustion is not going to be instantaneously happening as soon as the spark is created, but it takes some time in order to prepare themselves to start or to initiate the combustion. And therefore, AB, that whatever the crank angle it is taking between A and B, or between the spark, beginning of the spark timing, or between the spark timing and the start of the combustion, that is called ignition delay. That is called ignition delay. So it means start of the combustion and the spark timing is not the same point. There is a finite time between the spark timing and start of the combustion. That duration in terms of the time, millisecond, or in terms of the crank angle is called ignition lag. So what is ignition lag? You can say ignition lag is nothing but it is a time interval between the spark timing and the start of the combustion. When piston is reached at the point B, okay, then the combustion is going to be a start, and noticeable pressure can be detected, okay, with your sensors, and you will find it out that since it is a motoring pressure, there is no combustion. So what will happen? The pressure will fall down immediately as piston comes down. But the thick line is the firing pressure. The pressure is rising because of the combustion taking place inside the combustion chamber. So it will move up because of the combustion. The pressure and temperature inside the combustion chamber will move up even though piston is going down, and it will reach at that point. This peak pressure, okay, and the peak pressure occurs at the crank angle, corresponding crank angle. Both are very, very important parameter in order to determine the maximum torque output. That what you have also done the experiments. Two-third students have already done the experiments, and the rest of the students are going to do today itself. So what I'm saying, that peak pressure, the peak pressure point and its occurrence at which it is taking place is very important in order to maximize the torque output. So once the pressure inside the combustion chamber reach at the peak, the combustion pressure is almost combustion is almost finished, okay, and rest of the time the combustion is still going on, but since the piston is moving down, the volume of the combustion chamber is increasing, and the pressure peak, most of the combustion is also almost completed. So the what will happen, effective pressure inside the combustion chamber is going to be decreased. So the A to B, in which uh, there is a no combustion is taking place even though at the spark is created at point A. So that is called ignition lag. And then B to C, through where the start of the combustions to reach at the one maximum point C, that is called propagation of the flame. And C to D, in which pressure is combustion is still taking place, but the piston is moving down, and the peak pressure, the pressure due to the combustion is not so high also. So what C to D is called after burning. So when you see the P theta diagram of the SI engine combustion, you can easily divide the P theta zone into the three different zones. One is called ignition lag, that is A to B. B to C, we have a flame propagation region, and C to D is the after burning zone. Okay, that's the way the combustion takes place. Now, if you go into the details, combustion is really very, very complicated and very vast subject. Okay, in which there are so many parameters, flame propagation, what should be the rate of the flame propagation, what should be the slope rate at which the peak pressure should increase, okay, even though let us suppose the peak pressure is fixed, but the rate of the pressure rise, if it is very steep, then it is also not good. Then it depends upon your hardware that whether it can withstand such a steep rise in the rate of the pressure. So there are so many things how the flame propagation takes place. What are the factors that define that controls the ignition lag or the propagation of the flame or flame speed? What should be the what is the flame speed? Um, After burning, what are the parameters governing the after burning parameters? Because after burning is really very important from the emissions point of view. So all these things we can learn in the details, but that's fine. This much of information is enough at this point that it's very important that you must know the concept of the ignition delay, propagation of flame, and after burning. Do you have any question here? Any question regarding the combustion in SI engine? No? Okay, that's really very good. But I'm expecting that you should ask the questions that will be really very beneficial. So now what we are analyzing now, that we have a spark plug.
So I had a small question. So at B, both motoring as well as combustion takes place at the same time. Could you just explain that part?
This part, motoring pressure.
So as in the motoring happens when there's no combustion taking place in the chamber, and also it shows the case where combustion is also initiated at B. So I was really confused on how that.
Okay. That's fine. That's fine. I got it. See, the thing is, but how it has been plotted this curve, if I can explain to you, then the confusion will be clear. Initially, you have to run the engine in the motoring condition. Initially, you have to run the engine in the motoring condition. I hope it is clear in your mind that what is the motoring condition. Or let me clear it also. Motoring means your engine shaft is rotating. However, there is no combustion taking place inside the combustion chamber. So if there is no combustion is taking place, our engine shaft is rotating, how it will happen? Either we have to apply, it means we have to apply the external force, either in terms of the manual power, okay, however it is not possible to rotate the single cylinder engine, it might be possible to rotate, okay, but four-cylinder engine, it's not possible to rotate by hand. So we have to, what we have to do, your engine may be coupled with the motor, and then your motor will rotate the engine, even though there is no combustion is taking place. Or so, if the engine is rotating with the help of the external means here in terms of the motor, and then we measure the P theta variation and plotted it here, and that is what we have termed as a motoring pressure. Since there is no combustion is taking place in the motoring conditions, then what will happen? The pressure will rise as long as the piston will reach at the top dead center. And since there is no combustion is taking place, once the piston will come down from the top dead center to the bottom dead center, the volume is going to be increased and the pressure is immediately going to be decreased. You will find it out that motoring pressure is more or less, it will be very symmetric across the top dead center. So that's the way you can plot it, the motoring pressure. Okay. Now, we are not interested to run the engine with the help of the external means, because that is the negative torque we are applying. What we are going to do, we are start the fire. We are running the engine. The combustion engine is rotating because of its own power, because the combustion is taking place. Okay, and in that case, we are getting this curve that is thick line, and that we have named it as firing pressure. Firing pressure, motoring pressure. So when the combustion is taking place inside the combustion chamber, and at that time we are measuring the pressure and we are plotting it here. And then after that we are imposing both curve, firing pressure and the motoring pressure together. And then what we are finding it out, that in the firing conditions, even though a spark is taking place at point A, there is no deviation between the firing pressure curve and the motoring pressure curve, because the combustion is not initiated itself at this point, and therefore we are not observing any noticeable deviation of the firing pressure from the motoring pressure. But once the combustion is started at point B, then what will happen? The pressure will also rise because of the pressure, because of the combustion, and it will deviate from the motoring pressure, and then it will reach to the maximum pressure. That's the way it curve has been donated and has been plotted. The idea is to plot the motoring curve and the pressure curve together to show you that even though a spark has been created at point B, but the pressure in cylinder pressure is not changing with respect to the motoring. It means there is no combustion is taking place between these 2 points, and therefore we are naming it as the ignition lag. I hope it is clear, or something left.
It's clear, sir. Thank you, sir.
Okay, good. So ignition lag is a very important concept. That is what we have studied in our ideal cycles, that as soon as you provide, combustion is taking place instantaneously. It's not like that. You can see the P theta diagram here. Once you apply the spark itself, it takes the time, and then it is further taking the time in order to complete the whole combustion product. However, in an ideal cycle, what we have studied, that combustion is taking place at the constant volume. It's very fast, okay? But in actuality, it never happens. So the ignition lag concept, the combustion duration has a finite duration. It is not the instantaneous phenomena. It is a finite time. It takes the finite time, and then the after burning is also takes place.
So
Anything
will the
else?
P theta diagram change with the engine RPM?
Obviously, it will change. It is not the fixed parameter. It is not like that, irrespective of any pressure or RPM. We are going to how the RPM can be changed. RPM can be changed by changing the throttle. Okay. Once you change the throttle, then what will happen? The mixture strength is going to be changed in the combustion chamber. Mixture strength is most input energy is going to be increased or decreased, and depending on that, the peak pressure or its location, both is going to be changed. Okay, very good. Anything else? Any sort of the questions? I will always welcome. That that will always beneficial to the whole class.
So how can ignition lag be reduced?
Yes, that's a really very good question. How we can reduce the ignition delay? Because ignition delay, it is not a what is called, it is a positive thing. Okay, we want to have ignition delay as small as possible. Now, to know that how to reduce the ignition delay, first of all, we need to know that what happens during the ignition delay period. What are the physical phenomena take place during the ignition delay period? Okay, how this ignition physical phenomena affected using by the different parameters. and then if we can play with parameters, and then it's possible to increase or decrease the ignition. So
मेरे को हाँ ना यार, मैंने भी ये जनवरी फेब में लिया पिछले वाले, तो ऐसा लग रहा था यार बड़ा ले लिया, वो छोटा ही लेना चाहिए था, ये नहीं।
okay, so sometimes it happens. So what happens? Ignition delay period, we want to have a lower ignition. How it can be reduced? It can be reduced. Let us suppose one of the way, without going into the details, okay. Let us suppose someone is having ignition timing at 20 degree before top dead center, and somebody else wants to have the spark timing at 10 degree before top dead center. These are the two ignition spark timing. Mixture strength is going to be same. I'm not changing anything, okay. Mixture strength is remains same. Only thing I'm changing the spark timing. One is 20 degree before top dead center, another is 10 degree before top dead center. Can you guess that in which condition the ignition delay will be shorter, or it is not going to be affected? What is the view of the class? Just by changing the spark timing, one is 20 degree before top dead center, another is 10 degree before top dead center. Mixture strength, everything is the same. Whether the ignition delay period is going to be affected? Think about that. Yes, obviously it will going to be change, because when mixture is reaching towards the top dead center, what will happen? Its thermodynamic condition is going to be changed. The pressure and temperature will be higher at 10 degree before top dead center than the 20 degree before top dead center. In that conditions, when you are giving the energy, then what will happen? The mixture will ignite in the shorter duration compared to the if you are igniting, or if you are igniting it even before, much before than the top dead center. So one is the spark timing. Here itself you can see that if you can spark timing keep closer to the top dead center, the ignition timing, the ignition delay is going to be reduced. Second thing is that if you can increase the in cylinder temperature or pressure, then that will also create a favorable conditions when you are creating the spark at the same point. Then in that conditions also the ignition delay is going to be reduced. So there are several way that we can do the play with that, reduce the ignition delay period. For that, we need to know that actually what are the physical phenomena is taking place in the ignition delay period. And then once we know that these are the factors or these are the phenomena is taking place, then we can play with that parameters to reduce the ignition delay period. Very good. Anything else?
So how is the point D located on the graph?
D is not possible to read. There is nothing that we can say that D is at this point or this point. It's D after this point, okay. More or less when the combustion is almost going to be dead and there is a no sort of the power is contributing, then roughly we can say that is the end of the combustion or the after burning period. There is nothing straightforward the rules that we can put the boundary or the point D. More precisely, it can be done with the help of the combustion if you can visualize the combustions internally. But however, that is not possible. No, it's possible, but it's requires a very sophisticated kind of the experimental setting. So that's the way it can be done. Anything else? Okay, if not, that's fine. Only I want to give you the flavor that what we are going to discuss tomorrow. If you remember, during our beginning of the class, we have discussed about the compression ratio of the SI and CI engine. At that time, we discussed about that the compression ratio of the SI engine is lower than the CI engine. However, we further discussed or we come out that ideal uh, cycle has very much related on the efficiency of that engine cycle is related with the compression ratio. As we increase the compression ratio, the thermal efficiency of the engine will also increase. But however, we discussed also that the compression ratio in the SI engine is limited to around 12 or 12.5, maximum stretch up to the 13 with the different special conditions of fuel with that. The reason the question always comes into the mind that if you increase the compression ratio and we are going to get the maximum thermal efficiency, then why we are saying that the SI engine has limitations of the compression ratio? Which parameter, which physical phenomena is restricting the SI engines to extend the compression ratio? That is what we are going to get the answer of these questions in the next class, and that is what it is related with knocking that we are going to discuss. That is the abnormal combustion, that is knocking. Details will be discussed in the tomorrow class. Okay, thank you very much. In this class, if there is a section C is going to be there, is here. So today we will have 2 labs instead of the 1 labs because I will be out of stations, to make sure that all of you are present in the lab class in the second half. Thank you. So I am closing the session here. Okay.